In electrical systems, the concept of a line, specifically regarding disconnects, is crucial for safety and proper functioning. When determining whether a series of components still constitutes a single line, the number of disconnects plays a key role. The general guideline is that when a line contains 3 or more disconnects, it is no longer considered a single line. This distinction is important for several reasons, primarily related to overcurrent protection, fault current calculations, and overall system coordination. To understand why this is the case, let's consider the function of disconnects in an electrical system. Disconnects, also known as isolating switches or safety switches, are used to isolate sections of the electrical system for maintenance, repairs, or in emergency situations. They provide a visible break in the circuit, ensuring that the downstream equipment is energized, thereby preventing electrical shock or equipment damage. The National Electrical Code, or NEC, provides guidelines for the installation and protection of electrical systems, including the number and placement of disconnects. These guidelines aim to ensure that the system is both safe and reliable. Firstly, let's consider overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect the electrical system from excessive current flow, which can result from overloads or short circuits. When a line has multiple disconnects, the coordination of these overcurrent protection devices becomes more complex. Each section of the line, separated by a disconnect, needs to have its own overcurrent protection to ensure that a fault in one section does not affect the entire system. If there are 3 or more disconnects, it suggests that the line is segmented into multiple distinct sections, each requiring individual consideration for overcurrent protection. Secondly, consider fault current calculations. Fault current calculations are essential for determining the maximum current that can flow during a short circuit. This information is used to select the appropriate interrupting rating for overcurrent protection devices. The interrupting rating is the maximum fault current that a device can safely interrupt without failing. When a line has multiple disconnects, the fault current at each point in the line can vary significantly. This is because each disconnect introduces impedance, which can limit the fault current. When there are 3 or more disconnects, the variations in fault current become more pronounced, making it necessary to treat each section of the line as a separate entity for fault current calculations. This ensures that the overcurrent protection devices are properly sized to handle the maximum fault current at their respective locations. Thirdly, consider system coordination. System coordination involves selecting and coordinating overcurrent protection devices to minimize downtime and prevent unnecessary tripping. The goal is to ensure that only the overcurrent protection device closest to the fault trips, leaving the rest of the system operational. When a line has multiple disconnects, achieving proper system coordination becomes more challenging. Each section of the line needs to be coordinated independently to ensure that a fault in one section does not cause other sections to be unnecessarily de-energized. When there are 3 or more disconnects, the complexity of system coordination increases significantly, making it necessary to treat each section as a separate line. The NEC addresses these issues through various provisions. For example, NEC Section 240.21 discusses the protection of conductors. This section specifies the requirements for overcurrent protection of conductors based on their ampacity, which is the maximum current that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. When a line has multiple disconnects, the ampacity of the conductors between the disconnects needs to be carefully considered. Each section of the line needs to have overcurrent protection that is properly sized to protect the conductors in that section. The NEC also provides guidelines for the selection and coordination of overcurrent protection devices in industrial and commercial power systems in Article 240. Another relevant NEC section is 430.53, which covers the protection of motor circuits. Motor circuits often have multiple disconnects, such as a disconnecting means at the motor and a disconnecting means at the motor controller. The NEC specifies the requirements for overcurrent protection of motor circuits, taking into account the starting current of the motor and the potential for overloads. When a motor circuit has 3 or more disconnects, each section of the circuit needs to be protected in accordance with the NEC requirements. In summary, the rule that a line with 3 or more disconnects is no longer considered a single line is based on the need for proper overcurrent protection, accurate fault current calculations, and effective system coordination. When a line has multiple disconnects, each section of the line needs to be treated as a separate entity to ensure that the electrical system is safe and reliable. The NEC provides specific guidelines for the protection of conductors, motor circuits, and other types of electrical equipment, taking into account the presence of multiple disconnects. By following these guidelines, electrical engineers and contractors can ensure that electrical systems are designed and installed in accordance with industry best practices. The number of disconnects impacts the design and safety considerations of an electrical installation. Consider a scenario where a long run of conductors feeds several pieces of equipment in a manufacturing facility. If there are only 1 or 2 disconnects along this run, it might be reasonable to consider the entire run as a single line, with overcurrent protection located at the source. However, if there are 3 or more disconnects, perhaps to isolate individual machines or sections of the production line, the situation changes. Each of these disconnects introduces a point where the electrical characteristics of the circuit can be altered, and each downstream section requires its own assessment for proper protection. For example, imagine a conveyor system powered by a single electrical feed. If the conveyor system is divided into 3 segments, each with its own disconnect switch for maintenance purposes, this would constitute 3 disconnects. In this case, the electrical design would need to account for the possibility of faults occurring in any one of the 3 segments, and each segment would need appropriate overcurrent protection. This might involve installing circuit breakers or fuses at each disconnect switch sized to protect the conductors and equipment in that particular segment. Alternatively, consider a lighting circuit in a large office building. If the lighting circuit feeds multiple rows of lights, and each row has its own disconnect switch, the number of disconnects could easily exceed 3. In this case, the electrical design would need to ensure that each row of lights is properly protected and that a fault in one row does not affect the other rows. This might involve installing individual circuit breakers for each row of lights, or using a combination of circuit breakers and fuses. The application of this rule also depends on the specific requirements of the local electrical code and the authority having jurisdiction, or OJ. The AHJ is the entity responsible for enforcing the electrical code, and they may have their own interpretations or requirements regarding the number and placement of disconnects. It is always important to consult with the AHJ to ensure that the electrical system is designed and installed in accordance with all applicable regulations. In addition to the number of disconnects, the spacing between disconnects can also be a factor. If the disconnects are located close together, it may be possible to treat the line as a single entity provided that the overcurrent protection is properly coordinated. However, if the disconnects are located far apart, it is more likely that each section of the line will need to be treated as a separate entity. This is because the impedance of the conductors between the disconnects can affect the fault current and the coordination of overcurrent protection devices. Another consideration is the type of equipment that is being served by the line. If the line is serving sensitive electronic equipment, it may be necessary to provide additional protection against voltage transients and other power quality disturbances. This may involve installing surge suppressors or other power conditioning equipment at each disconnect. The presence of this equipment can further complicate the electrical design and make it more necessary to treat each section of the line as a separate entity. The rule regarding the number of disconnects is not a rigid one, and there may be exceptions depending on the specific circumstances. However, as a general guideline, it is prudent to treat a line with 3 or more disconnects as multiple separate sections requiring individual analysis for proper overcurrent protection, fault current considerations, and system coordination. This approach helps ensure the safety and reliability of the electrical system while also complying with the requirements of the NEC and other applicable codes and standards. By adhering to these principles, electrical professionals can create safer and more efficient electrical systems for a wide range of applications. In practical terms, determining when a line is no longer considered a single entity necessitates a comprehensive understanding of electrical engineering principles. This involves a thorough analysis of the circuit's configuration, the characteristics of the loads being served, and the potential fault conditions that could arise. The goal is to ensure that the electrical system is robust enough to withstand these fault conditions without causing damage to equipment or posing a safety hazard to personnel. When evaluating the number of disconnects, it's important to consider not only the quantity but also their placement within the electrical system. A disconnect located near the source of power will have a different impact than one located further downstream. Disconnects placed closer to the source will typically affect a larger portion of the electrical system, while those placed further downstream will have a more localized impact. Additionally, the type of disconnect being used can also influence the decision-making process. Some disconnects are designed to interrupt fault currents, while others are not. Disconnects that are not designed to interrupt fault currents must be used in conjunction with overcurrent protection devices, such as circuit breakers or fuses, to ensure that the circuit is properly protected. The NEC provides detailed guidance on the selection and application of disconnects, including requirements for their interrupting rating, voltage rating, and enclosure type. It's essential to consult the NEC when designing an electrical system to ensure that the disconnects are properly selected and installed. Beyond the NEC, other industry standards and best practices can also inform the decision of whether a line should be treated as a single entity or multiple separate sections. For example, the Institute of Electrical and Electronics Engineers, or IEE, publishes a variety of standards related to electrical power systems, including standards for overcurrent protection, grounding, and power quality. These standards can provide valuable insights into the design and operation of electrical systems, and they can help electrical engineers make informed decisions about the number and placement of disconnects. Another important consideration is the potential for future expansion or modification of the electrical system. If the system is likely to be expanded or modified in the future, it may be prudent to design it with multiple disconnects from the outset. This will make it easier to isolate sections of the system for maintenance or upgrades without disrupting the entire system. Furthermore, the complexity of modern electrical systems often requires a more nuanced approach to disconnect placement and protection. With the increasing use of electronic devices and sensitive equipment, power quality has become a critical concern. Voltage sags, swells, and transients can damage sensitive equipment, leading to downtime and costly repairs. Disconnects can play a role in mitigating these power quality issues by allowing for the isolation of equipment during periods of instability. In addition to the technical considerations, there are also practical aspects to consider when determining the number and placement of disconnects. For example, ease of access and maintenance are important factors to consider. Disconnects should be located in areas where they are easily accessible for inspection and maintenance. They should also be clearly labeled to indicate the equipment that they serve. Ultimately, the decision of whether a line should be treated as a single entity or multiple separate sections is a complex one that requires a thorough understanding of electrical engineering principles, industry standards, and best practices. By carefully considering all of the relevant factors, electrical engineers can design safe, reliable, and efficient electrical systems that meet the needs of their clients. Therefore, the 3 disconnect rule serves as a general guideline. Practical application necessitates a case-by-case engineering evaluation.